Good morning, everybody.
Good morning.
So a couple of things before we get started on today's lecture. First is, I have posted your interim grades in SOAR. So when you go and you look at those, that is everything up until Wednesday. I have not graded Wednesday's quiz yet, so that does not include Wednesday's quiz. So when you go in and look at your interim grade, just know that. So that most recent quiz is not included in that score. Overall, I'm quite happy with the interim grades, but I do want to caution that there is still plenty of time to either fall back or to move forward, right? So we want you all to move forward. So if you have a really good score at interim, just remember there's plenty of time for that to erode if you let it. So don't get into that boat. So that's where we're at with interim grades. When you go and talk to your advisors, right, you should at least have conversations about interim grades. And just remember we have a couple more tests left, and we have plenty of quiz opportunities, and we're pretty much so out of extra credit situations. So from now on, you know kind of what's coming down the pipe. So last Monday, a week ago, I talked about doing a demonstration, and I've got this videoed from years ago, so we'll go through the video in just a moment. But what we're going to look at is we're going to look at the hydrolysis, which is an SN1 reaction of tert-butyl chloride in the presence of water. Okay, and so tert-butyl chloride is not very water soluble, so we add just a little bit of acetone to make it soluble. Okay, it's really not the solvent; it's what we call a co-solvent. The solvent is really water. And when you mix these things together and shake them up and let them, you'll make this alcohol, plus the byproduct is hydrochloric acid. And we'll do the same thing for tert-butyl bromide. Again, same conditions. And we'll get the same alcohol but a different acid. We'll get HBr. What would you think about the reaction rates of these? Do you think they'll be equal or different? They will be different. And they'll be quite a bit different, actually. Okay? So how would we monitor this reaction? Well, it's actually pretty easy to do because we're generating acid, right? And so what we have done in the demonstration is we have added just a little bit of sodium hydroxide to the solution just to make it slightly basic. And we've added a few drops of phenolphthalein. So if you think back to Gen Chem, right, when you had phenolphthalein and base, what was the color?
Pink.
It was kind of pinkish, right? What you're seeing there on the video. So as we're generating acid in this reaction, what do you think is going to happen to the color?
Go to clear.
It'll eventually go colorless, right? Once all the base has been consumed, it'll go colorless. And what we're going to use is we're going to use that color change as an indication for reaction completion. Okay, it's not completely over at that point, but we're gonna use that. So what you're looking at in the video, and I'll play it here in a minute. It doesn't have any sound with it, but you see the two bottles in the back, and you'll see that they are filled exactly the same amount with this pink solution, which is a mixture of water and acetone, and it's by far more water than acetone. And they're pink. And then the little vials in front are solutions of tert-butyl chloride, which I believe is on the left. You can see it says Cl, and then the one on the right says Br. That's the tert-butyl bromide. What I'm going to do is and that is my hand in the video, we're going to dump those in, we're going to put a screw cap on them, we're going to shake them, we're going to watch and see what happens. So let's see if we can see what happens in this particular video. So relatively, when you take those seconds and you do the division, you see that it is 8 times faster for the bromide to react than the chloride to react. But the mechanism is exactly the same, right? So why is the bromide more reactive than the chloride?
Was more reactive, sir?
Why is one more reactive than the other? Why is this 8 times faster than this?
Electrons.
Electrons are always involved in chemistry, right? But why?
Bromide is a better leaving group, as the video says.
It is a better leaving group, but why?
Why?
Does it have to do with like bond strength, like if it's shorter along the person?
Okay, that's true. So one would expect the carbon-bromine bond to be longer than the carbon-chlorine bond, and so you have a weaker bond. Okay, that's true. What else?
Bromine is larger than chlorine.
Bromine's larger than chlorine. That's true.
So it's more acidic.
It is the conjugate base of the stronger of the two acids. That is correct. Same things that are correct, but there's still more to it. So what does that tell us as we go down the periodic table in terms of leaving group?
They get stronger the further we go
The
down.
further we go down. In fact, if I had tried tert-butyl iodide, it would have turned it pink before I could ever get the cap screwed on. We couldn't really take a good time measurement. Okay. So we didn't do that. So we picked chloride and bromide. Right? But I know that now that as I go down the family, the leaving group gets better, and it has to do with the fact that we have a weaker bond. It has to do with the fact that we have a bigger atom. So bigger atoms like to be better leaving groups because they can handle that negative charge better on the leaving group, right? And it turns out that bromide is the conjugate base of the stronger acid, which means that bromide is the weaker base. Weaker bases make better leaving groups than do stronger bases. So in fact, if I had taken tert-butyl fluoride and put in there, along with tert-butyl bromide, we'd still be watching the video. The tert-butyl fluoride just won't leave over a reasonable period of time. And in fact, if I'm guessing, we could probably come back next week and it would still be pink. Okay, so it's a very, fluorides are very bad, or fluoride, excuse me, is a very bad leaving group, relatively speaking, right? So today, why is my front TV not working? I have no idea. We'll just have to deal with the screen. So today we're going to talk a little bit about why some carbocations are more stable than others. We're going to talk about things that affect SN1 and SN2. We just saw some of it, right? And so we know that the leaving group matters. We'll talk a little bit about that. And then we're going to talk a little bit about elimination reactions and hopefully fix everything up. And it's not chapter 6.1 to 6.18. I just didn't change the title on the old slides. This is the last part of 7, right? So what we just saw, right, was we were reacting tert-butyl bromide with a nucleophile. Now it's not this particular reaction. This is a different reaction, right? But the tert-butyl bromide is the same. And we know that what's happening here is an SN1 mechanism, and the carbon-halogen bond breaks and we end up generating the carbocation. That is the slow step of the reaction. Why is that the slow step?
Because the bonds are breaking in the corner, and it's the highest energy.
Okay, true, it is the highest energy, but why is it the highest energy?
Because
When the bonds are breaking, you're right, so it's going to take energy for that to happen.
it's by creating the carbocation.
Okay, you're on the right track. What is it about the carbocation that makes that the slow step?
It's unstable
Why is it unstable?
because the carbon only has 3 bonds and it has a positive charge.
Okay, which means it isn't satisfying what?
Bond
the octet rule, right? And so all of the things that you said were correct. We were just trying to dive a little deeper. This is the slowest step. Once you have a carbocation, if there is a nucleophile around, it will react with that nucleophile. And in this case, we are using acetate anion as a nucleophile. It's an oxygen with a negative charge. That will attack the carbocation, and we form the new carbon-oxygen bond. This is the fast step. Why is it fast?
Smaller.
Because it's what?
Smaller.
It's smaller? What do you mean by that?
Which
It attacks-
one which I would also.
Okay.
It attacks quickly because it's on, like, the carbocation state doesn't last long because it's very unstable, so.
Okay.
Other least just attacks.
Okay, that's good. What do we know about bond making steps?
Releases energy.
They all release energy, right?
Yeah.
So they're going to release energy. It's going to go to a more stable product. But it turns out that the transition state for this second step is actually very small. It's a very small energy of activation for all the reasons that Selena just said, right? We're going from something that's positively charged to something that's neutral, something that doesn't have an octet to something that does have an octet. Okay, and so while this is a two-step process, only one step controls the rate of the reaction, and it's the slow step. You will always hear me refer to that as the rate determining step of the reaction. Okay? So if Colton wanted this reaction to go faster, he's just going to have to increase the amount of starting material, right? Adding more acetate doesn't increase the rate of the reaction because it's not in that rate determining step. It's not the slowest step. Okay, so it's only dependent on the alkyl halide concentration. What we know is that the rate of an SN1 reaction is going to depend on the type of halide involved. Now let's assume that X is all the same halogen here for the moment. Let's just pick on bromide. Let's say we have methyl bromide, some kind of primary alkyl bromide, some kind of secondary alkyl bromide, and some kind of tertiary alkyl bromide. Okay? What we know is that the rate of reaction will be very, very quick for a tertiary alkyl halide. If I had a secondary alkyl halide, the reaction would actually be quite slow. I could have done the same experiment with a tertiary and a secondary alkyl halide to show you that as well. And what we would have found is that the tert-butyl bromide again would have reacted, in 32 seconds, whereas this one would have probably taken a couple of minutes. Okay, so what does that tell us? That tells us that really what we're going to be able to do is SN1 chemistry on secondary or tertiary alkyl halides. It turns out that primary alkyl halides and methyl alkyl halide, or methyl halides, I should say, do not undergo SN1 reactions. They'll undergo SN2 reactions, but they won't do SN1. Okay? So if we're going to have an SN1 reaction, we know it's got to be a secondary alkyl halide or tertiary alkyl halide. Okay? This is exactly the opposite of what we see in SN2. SN2, pretty much so, is going to be methyl, primary, and secondary. Tertiary alkyl halides do not do SN2 chemistry. Okay? The nucleophile just can't get in there to kick out the leaving group in that rate determining step. It's too crowded. We call that steric hindrance. Okay? And so what we know from all of this is that the SN1 mechanism, we say this is a first order reaction. That meaning that the rate is only dependent on the concentration of alkyl halide. Only one species. Okay? It is a two-step mechanism. Right? We know that the stereochemistry of the reaction, it goes through a planar carbocation, and the nucleophile can either attack from the top or the bottom. And so we can get racemization. We talked about that a little bit before, right? And we know that the more R groups that we have attached to the carbon with the halogen, the faster the reaction. And we know it's going to be tertiary is much greater than secondary. These really don't undergo SN1 chemistry at all. Okay? And we can look at these so-called electrostatic potential maps to see that. Okay? So if you think about it, a reaction goes faster because the energy of activation is lower, right? Everybody agree with that? So it must mean that the energy of activation to generate a tertiary carbocation is lower than to generate a secondary carbocation. That makes sense, right? And these electrostatic potential maps tell us why. Blue is positive charge. What do you see in the tertiary? Do you see a lot of blue in the middle? No, it's kind of greenish colored, right? It turns out that the more alkyl groups you have attached to a carbocation, the more stable it is and the less overall positive that carbocation is. Yes, it has a formal positive charge, but the more alkyl groups you add to it stabilizes that charge. Okay? Notice methyl. You essentially can't generate a methyl carbocation. Okay? Now, George Olah at University of Southern California back in the, I think it was the 1970s, he did it using a mixture of what he called magic acid. And he won the Nobel Prize for doing it because nobody thought you could generate a methyl carbocation. And for all practical purposes, you can, right? You have to do some really unique kind of things to trick Mother Nature into doing it. But so what you need to know is that a tertiary carbocation is more stable than a secondary carbocation, is much, much, much more stable than a primary carbocation, which is much, 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 much more stable than a methyl carbocation. And in fact, what we can say for the purposes of this class is that methyl carbocations and primary carbocations do not exist. Okay? And I told you just some examples where they have been made to exist, but they're not really relevant in the real world. Okay? So, you need to know your carbocation stability. We also know that carbocations will rearrange to more stable carbocations, right? And we talked about moving of alkyl groups and hydrides in the previous chapter where we were talking about some of that stuff, right? And so you always got to keep that in mind as well. So the rule is anytime you generate a secondary carbocation, ask yourself if it can rearrange to a more stable one. And if it can, do it, right? Here's the reason why adding alkyl groups to a carbocation stabilizes it. It's called hyperconjugation. Okay? What you see in the methyl carbocation, if you were to draw it out, is these CH bonds are all in the plane of and orthogonal to the orbitals of the p orbital of the carbocation. These electrons can't do anything to help stabilize this carbocation. However, when you look at the orbitals of an alkyl group that's adjacent to it, right? So here's the bonding orbital for the alkyl group that's attached, okay? And there's electrons in that orbital, right? And through space, a little bit of overlap occurs, and these electrons can actually help stabilize that carbocation. That's why you saw on those electrostatic potential maps, the more alkyl groups you added, the less blue color there was, because these electrons are donating in just a little bit to stabilize that. And so all of that to say, what you need to know is that tertiary carbocations are more stable than secondary. Okay? So, we'll skip that one. Pardon? Skipping the Hammond Postulate.
The Hammond Postulate?
Yeah, the Hammond Postulate. I don't think your book talks about it. Basically what it is in just this one slide is that the transition state mimics the stability of the intermediate. So the more stable that intermediate carbocation, the lower the energy of activation. Okay? So if you had a carbocation that was here, let's say this is a secondary carbocation, this is a tertiary carbocation, what you can see is the energy of activation is different for these two, and so that's why you end up with the different rates of reaction. Okay?
This isn't going to be on test.
The Hammond postulate, I will not use those words, no. All right, so we know that the nature of the alkyl halide matters, right? Tertiary alkyl halides are going to react faster. We also know that the leaving group matters. So a tertiary alkyl chloride will be slower than a tertiary alkyl bromide. Okay? We also know that the nucleophile can matter in some cases, and it can matter when we're talking about the SN2 reaction. Okay? It doesn't matter in the SN1 reaction. because it's only generating that carbocation that's the slow step. But in an SN2 reaction, right, the nucleophile has to come in at the same time that the leaving group is leaving. Both of them are involved in that single step of the reaction, right? And so in SN2 reactions, the nucleophile does matter, okay? And so here's a few rules that you need to know about, okay? So if you have two nucleophiles that have the same nucleophilic atom, that is the atom that's making the bond, the stronger base is always going to be the stronger nucleophile. So for example, if I had hydroxide and acetate, just draw them out. HO, right? Lone pairs of electrons minus versus the acetate ion. Both of these atoms are going to be the nucleophilic atom. And in both cases, it's oxygen, right? Both of them are oxygen. Both of them have a negative charge on it. You might predict that they would have the same reaction rate, but they don't, okay? It turns out that the one that it belongs to the strongest base is. Hydroxide is a stronger base than acetate. Okay? We can look at that up by looking up the pKa tables, right? So the conjugate acid of hydroxide is water, and it has a pKa of, let's just call it 16. And acetate is the conjugate base of acetic acid, right, vinegar, and it has a pKa of 4.8. Let's just call it 5. Right, so which one of those is the strongest acid, water or acetic acid?
Acetic acid.
Yeah, by quite a bit, right? And so we know, right, the stronger base is going to be the stronger nucleophile, right? And so this has to be the stronger base based on those comparisons. So if I did a reaction, an SN2 reaction, where I had hydroxide and acetate, a hydroxide reaction would work much, much faster, okay? So here we have an example of if we have the same nucleophilic atom, but one is charged and one is neutral, the negatively charged nucleophile will always be the stronger nucleophile. So if you did the reaction of hydroxide functioning as the nucleophile and water functioning as the nucleophile, hydroxide reaction would work faster. And that makes sense because it has a negative charge, right? So negatively charged nucleophiles are almost always the stronger nucleophile than is its conjugate acid, right, which is water, right? Oh, it just decides to work. Good. As you move from right to left across the row of a periodic table, nucleophilicity increases as basicity increases. So as you go from right to left in a period, you're going to have increasing nucleophilicity. Okay, so CH3 minus is a very strong nucleophile. NH2 is less. Hydroxide is less. Fluoride is less. Okay, so as you move from left to right, remember, we become more acidic, right? Which means by definition you become less basic, right? So that's how this all comes out. So if we had hydroxide functioning as a nucleophile and fluoride, we would predict that the hydroxide would react faster than the fluoride as a nucleophile. And that's exactly what we would see in these types of reactions. Okay? All right. So let's do a little group exercise here. We're going to do what we call a competition experiment. Okay? We're going to do a competition experiment. We're going to take one alkyl halide and we're going to put it in solution with two nucleophiles. And let's predict what the major and minor products are going to be. Right? So take 4 minutes, work with your partners. You can see in table 7.2 of your book on page 202, you can get some hints there. Okay? See what you come up with.
that OH was already a baseline stronger than.
Yeah.
Acetate.
Like hydroxide is the main thing. Right. So acetate is just a product. So like from that in itself.
Hey, you know what? Sunday and the weekend, because my life is just like I
She kind of more so trying to figure out.
Yeah.
school is just
Kind of a little bit fish out of water for this one because I know it's the first day.
Yeah, it's the one.
Oh, wow.
I bet Jason knows what's going on.
I haven't caught up yet. Out in the open.
Really, Megan?
Okay. Let's take a look at this. This is how I like to think about these problems. Okay? I've got one starting material, one alkyl halide, in one flask, but I've got two nucleophiles in that flask. So really within that one flask, I've got two reactions going on. So I can split it up into two reaction arrows, right? I can make life simple. I don't have to think about it as all just being thrown together. In this particular case, right, it's the acetate anion that's going to function as the nucleophile, right? And so you're going to, nucleophile is going to add, leaving group is going to leave, all in the same step. And you're going to make this molecule. Okay? Plus, of course, sodium bromide. Does that make sense to everybody?
Yeah.
In the second reaction, the hydroxide is going to be the nucleophile. So the hydroxide is going to attack the carbon and the leaving group is going to leave. And I'm going to make this molecule plus sodium bromide. Okay? And so what would you predict to be the major product? The alcohol on the left or the ester on the right?
On the left.
You would predict that the alcohol would be the major product, and you would predict that why?
Because alcohol is more basic, or like it's a good, like in that table, it said that OH was in like the good section.
Oh, okay. So the hydroxide being a better base. That's right. So we're dealing with the same nucleophilic atom. They both have a negative charge. This is the stronger base, so it's going to be the better nucleophile, right? So that's how we do that. And in fact, this is what we would do. We would predict that the major product would be the alcohol, and the minor product would be the ester shown here, okay? These are called competition experiments. This is how we know a lot of the stuff that we know. We see how things compete relative to one another, and that tells us something about the reaction mechanism, okay? So these are so-called competition experiments that so-called physical organic chemists, which I was at one point, do this type of stuff to determine mechanism. Okay, mechanism is a very important thing to understand, right? Now, the nucleophile, it depends on what kind of solvent you're in. Yes, ma'am?
Is that NaBr, is that gonna be positive and negative?
Yes, I just drew it as the salt. Yeah. Yep, it's a salt. Okay. So if you have a nucleophile, it turns out that the solvent matters. Up to this point, we've just kind of assumed that the solvent was the solvent and it was just there to mix everything together. But the solvent matters, okay? If you use different solvents, you can actually see differences in the reaction. So let's suppose we're using sodium bromide, okay? And we want bromide, Br minus, to be our nucleophile. Okay, so let me draw another reaction up here. Let's say I've got some alkyl halide. We'll just use X, where X is not bromide. And we throw this in with some sodium bromide. And what we get out of this is an alkyl bromide plus NaX. Okay? We can do that kind of reaction. And it turns out that the solvent that's used, which I don't have indicated here, will determine the rate of the reaction. If I use something like water, okay, this is what water does to sodium bromide. This is why salts dissolve in water, is because of these interactions between the solvent and the components of the salt. And so sodium, of course, has a positive charge. So the oxygen atoms of the water are surrounding themselves around the sodium, and you're getting these so-called coordination bonds. You don't need to worry too much about that, but it's an ion-dipole interaction, okay? So we know that water is polar, right? It's got a dipole, it's got a negative side to the dipole. Negative likes positive, and so this is how the water surrounds itself around sodium. But is sodium the nucleophile? No, so it doesn't matter, right? But notice what's happening in water with bromide. Bromide has a negative charge, and water also has a dipole that on part of it's positive, right? And that positive part of the dipole is around the hydrogens, and so you form hydrogen bonds between water and the bromide. Is that going to interfere with the nucleophile doing its chemistry?
Yeah.
Absolutely. Remember, the atoms have to actually come into contact for a reaction to happen, right? How can bromide get into contact with this carbon if it's surrounded by water? Can it? Not easily. What would have to happen?
You have to change the polarity of them.
Well, that's getting a little ahead, but you're not, we'll see an example in another solvent. What would have to happen?
Will one of the water ones have to break to make space for another one?
Okay, so we'd have to shed all that water to make the bromide kind of naked, okay? So it would react. And it's in water. Is that going to be easy to do? It's not going to be terribly easy to do. And what do we know about bond breaking events?
They release energy.
Bond breaking?
Need energy.
No.
They need energy, right? So to remove all of this water from around bromide for it to react, it's going to take a lot of energy, right? So this reaction in water is actually going to occur, but it's going to occur slowly. So what can I do to speed the reaction up?
Change the solvent.
I can change the solvent, right? And so it turns out we can do that, okay? And so let me just get to this, and then we'll go back and talk about those. I kind of have these out of order. So here's an example of where we're using sodium bromide as the solvent, or as the nucleophile, excuse me. But now we're using an organic molecule as the solvent. This is acetone. Okay, we'll talk about that in just a moment. What you'll notice is that it still solvates the sodium, but notice what's happening to the bromine. There's no hydrogens for it to form hydrogen bonding with. So the solvent is very loosely associated with the bromide. It's not tightly bound to it. This bromide is actually more quote unquote naked, and it's a lot more reactive. And so if you did this reaction in sodium bromide, or with sodium bromide and acetone, you would find that it's 10 to 50 times faster than if you did this in water or some type of alcohol that has an OH, okay? And so we have to think about solvents, okay? And so you can have what are called polar protic solvents. Water is a perfect example of a polar protic solvent, okay? So polar protic, I just said that water is a perfect example. It's polar because we've got polar bonds, right? And we've got a dipole that runs in that direction. Okay? What does this word protic mean?
Protic means
Protic. What does it sound like? What else in chemistry sounds like
Protons.
protons, right? Another name for hydrogen, organic chemists call them all the time, we call these protons, okay? It's another name for hydrogen. Proton is just hydrogen without an electron, right? But this is a polar protic solvent because it has hydrogen atoms that are attached to electronegative things like oxygen. So all polar protic solvents will be polar by definition, but they will have hydrogens that are bound to oxygen, they will have hydrogens that are bound to nitrogen, or they will have hydrogens bound to fluorine, okay? Which really you can't have that one here, but it's true. So whatever else is attached to these, we don't care. But as long as you have an NH or an OH, you have what's called a polar protic solvent. Okay? These things can form hydrogen bonds with the nucleophile. That's the important point.
Can you kind of say that again? Like,
Which part?
like just kind of summarize that again.
Okay, so let's just use some examples. Water is a polar protic solvent. Would you consider methanol a polar protic solvent?
Yeah.
Yeah, it is. Alcohols are also polar protic solvents. So things like this are all going to be polar protic because we have that OH bond, right? We can also have solvents that look like amines. Those could also be polar protic solvents because we have the NHs, okay? They are polar. They have dipoles, but they are polar protic solvents.
So
Okay?
any molecule that has those polar protic bonds that you just drew is polar. And what does that mean? Like, what is?
It means that they are going to let the reaction work, but it's going to be slower. The reactions will be slower in polar protic solvents. SN2 reactions are always slower in polar protic solvents, okay? Because the nucleophile has the solvent wrapped around it, okay? Methanol, ethanol, whatever, will wrap itself around the bromide or whatever the nucleophile is because it's negatively charged through the hydrogen bonding of these hydrogen atoms, okay? Not all hydrogen atoms do it. The hydrogen atoms attached to carbon won't do it. It has to be a hydrogen attached to either oxygen or nitrogen, okay? Because you have to have that electronegativity difference for this to work. Carbon and hydrogen have about the same electronegativity, so there's no dipole, okay? And what we'll notice is that as we go down a family, right, we'll see that the nucleophilicity actually increases. Fluoride is a poor nucleophile. Iodide is a great nucleophile, but only in polar protic solvents. It's exactly the opposite in other solvents, okay? So iodide is a great nucleophile in methanol or water. Bromide is a little less good, but it's better than chloride, so on and so forth, okay? And it has to do with size. So the bigger the atom, when those waters are around it, the water can come off a lot easier on a big atom than it can a very small atom, okay? You need to commit to memory all of these 6 examples of polar aprotic solvents. You need to know them, okay? Polar aprotic. Why is acetone polar aprotic? Let's start off with the polar part. Why is it polar?
Because of the oxygen, like it has more
Yep.
negative that way.
Yep, because of the carbon-oxygen bond, right? You're going to have a polar component to it. So there's that. Now, why is it aprotic? What does that mean?
No hydrogen bonds.
Can't form hydrogen bonds, right? Notice the oxygen has no hydrogens to it, right? So it can't form hydrogen bonds with the nucleophile. It's a polar protic solvent. Acetonitrile, again, is a polar protic solvent. Polar because the carbon-nitrogen electronegativity differences, right? But nitrogen has 0 hydrogens attached to it, so it's aprotic. A, whatever, means without. Okay, so protic is with a proton. Aprotic is without. Tetrahydrofuran, one of my favorite solvents. Okay, this is actually a polar aprotic solvent, right? Because the carbon-oxygen bonds, there are electronegativity differences. You end up with a dipole that runs in this direction, and you have no hydrogens on the oxygen atom of tetrahydrofuran. Dimethyl sulfoxide. This is one that you may or may not be particularly familiar with. DMSO is used in a lot of creams for like sore muscles to get the medicine through the skin. It is a nice polar aprotic solvent. I hate working with it because it has a very high boiling point. It's hard to get rid of, but it does its job. And then this is called dimethylformamide. Okay, it is a polar aprotic solvent. Obviously, you can see why it's polar, but again, both the oxygen and the nitrogen, neither one of those atoms have a hydrogen attached to it. And then this is hexamethylphosphoramide, also known as HMPA, which is a nice polar aprotic solvent. Again, none of the heteroatoms, the oxygens or the nitrogens, have hydrogen attached to them. Okay. If you're thinking 6 is too much to memorize, definitely memorize the first 4: acetone, acetonitrile, THF, and DMSO. Those are the ones you absolutely need to know. Okay? Those are the most common used in these types of reactions. Dimethylformamide is another pain, and HMPA is actually quite carcinogenic, so people don't use it as much as they used to.
Are we going to be allowed notes on all our tests?
Pardon?
Are we going to be allowed our written notes
Yeah.
on all
Yeah,
our tests?
for every test.
Even on mine?
Huh?
Even on mine?
Yeah, sure. Even the final. I get to use my notes all day. Why can't you use
Do you
yours?
teach biochemistry?
Nope, I do not. I do not.
So it's like,
Can you next semester?
Nope.
come on, you know you want to.
I don't want to. And so we just talked about this. The reason that the polar aprotic solvents favor the SN2 reaction is because they don't solvate the anion or the nucleophile very well. And so it's easy for them to get out of the way, if you will, for the reaction to occur. They're not bound strongly by a hydrogen bond. Yes, they surround it, but they get out of the way pretty easily because they don't have that strong bond. And we say that these things are naked. Okay? Now, I know, organic chemistry is kind of weird. Organic chemists attacks things, and things are naked or clothed, and that's just the way it's evolved. But so anyway, if you hear me say a naked anion, you know that I mean that the anion just doesn't have a lot of salt around it. Okay.
And would you say that, like, is it going to be specified for us, like, oh, this is a naked anion, or is it like, are we supposed to know that certain?
Well, you need to know the combinations, right? So if I give you a reaction on an exam, and I haven't put the exam together yet, so I don't know what I'm going to ask yet. But let's say I give you 2 reactions, and I ask you which one of these reactions will be the fastest, right? And it was, let's say, an SN2 reaction, and you had the same nucleophile, but the solvent was different. You would need to know the rules of polar protic versus polar aprotic, and which one favors. Okay.
Do we have like a table or something for like the common solvents and like the increasing?
There's a table in your book that talks about that gives the common polar protic and polar aprotic solvents. Yeah, and that's pretty much the one I want to stick to. It's pretty much the tables that I just showed you. Yeah, maybe a little different. Okay. All right, so let's do another prediction. This is another kind of reaction, except this time it's not really a competition reaction. It's two separate flasks. All right, so Jason took this alkyl bromide and he puts it in one flask with the strong nucleophile hydroxide, and he puts some of it in another flask with water, which is a weak nucleophile, and then lets the reactions go to completion. What are the products going to look like?
The OH
I'll just say this, the products are actually the same.
Yes.
They're both alcohols. Both products will be alcohols.
So I need an extra hydrogen.
Not an extra hydrogen. Do we have stereochemistry in this molecule?
Yeah.
What do we know about the methyl group and the bromide?
There's cis.
They're cis to one another, right? They're both coming out of the plane of the board, right? So if I have a strong nucleophile, is that going to be SN1 or SN2, you think?
It's gonna be SN2.
Why?
Because in SN2 the nucleophile attacks.
Very good. In that rate determining step, the nucleophile has to attack the carbon as the leaving group is leaving, right? So what you would predict for this particular reaction, right, we've got the methyl group coming out of the plane of the board. I've got the bromide coming out of the plane of the board, the bromine, excuse me. And now hydroxide is going to attack. How's it going to attack? How would I draw that arrow?
To the carbon below the bromine.
Be on the back side of the board, right? And what happens here?
The bond breaks.
Yeah, so that's an SN2 reaction, right? What would the stereochemistry be of that? I didn't do anything to the methyl group, so it's still coming out of the plane of the board, right?
The OH would be from the back of the.
It'd be from the back, right? A little bit or completely?
Completely.
Completely. We call this inversion of configuration, right? There's no R or S here because we don't have a chiral center. But we would know through our magic microscope that the methyl group and the OH would be on opposite sides in this reaction. So we know that this has to be an SN2 reaction.
How do we know then that it's an SN2 reaction?
Because an SN2 reaction, the nucleophile has to come in from the backside. So strong nucleophiles typically favor the SN2 reaction. Now we look at the second flask. Right? And now we're using water as the nucleophile. What's going to happen?
It's gonna make a carbocation issue.
Why?
Because the nucleophile is not strong enough to do an SN2.
That's right. Weak nucleophiles do not favor SN2 reactions. Weak nucleophiles favor the SN1. So the slow step is what?
The breaking of the bromine beads.
That's right. And so we end up with an intermediate carbocation that is secondary. Secondary carbocations are okay. Can it rearrange to a more stable carbocation?
Yeah.
No. If I move these, I still get a secondary, so it just stays there.
Oh, yeah.
Yeah, it doesn't really result in anything, right? And so I'm going to put this in bracket. Okay, just to show that it's an intermediate, right? That's not the product of the reaction. So now what happens?
The H2O attacks from both sides.
That's right, it can either attack from the back, which I'm going to use by that dashed arrow, or it can attack from the front using the solid arrow. And when that happens, right, we end up with two products. We end up with exactly the same product of the SN2 when it attacks from the back. If I can draw something, there we go. OH. And we also get this. Are those the same product? They are not. They are different. They are. It's not racemic because we don't have a chiral center,
Oh.
but it's kind of like that. Yeah, because this group and this group are exactly the same on this molecule. This carbon is not chiral. Okay, and so these are trans to one another, and these are cis to one another. Okay? But very different. I mean, those are physically different alcohols. We can again use our magic microscope, or we can do some sort of a experiment to determine one over the other, which we're not going to talk about today. Okay? So strong nucleophiles favor.
SN2.
Weak nucleophiles favor
SN1.
SN1. Okay. Polar aprotic solvents favor. Polar aprotic favor.
SN.
Polar aprotic favor SN2. Again, because we want that nucleophile to be naked, right? And polar protic solvents favor SN1. That's right. Okay?
Okay, wait, so SN1 is polar protic?
Polar protic favors SN1. Now, if I give you, let's say, a primary alkyl bromide and a nucleophile in water, would that be SN1 or SN2?
Well, it won't be SN1 because it's primary alkyl.
Yeah, so if I gave you ethyl iodide and I told you to react that with sodium hydroxide in water, you're still going to get that alcohol, but it's not going to be SN1 because this can't generate a primary carbocation. It would just be a really slow SN2, right? Okay.
Why can't it make the carbocation?
Because primary carbocations don't have enough groups around them to really stabilize that carbocation. The energy is just too high for it to really form. So it would much rather shed all of the solvent from around the anion to form the bond to an SN2 reaction than get all the energy it needed to generate a carbocation.
Yeah.
Okay? Chemistry really is a lazy thing. Nature's lazy. Nature's not going to take a high energy path to anything. Okay? It's always about getting to something more stable. Okay? And since we know that the transition state of the SN2 mechanism, right, depends on the leaving group, and we also know that that the transition state for the SN1 mechanism also involves a leaving group, we know that the better leaving group is always going to favor both of them. An SN1 reaction will be favored if it has a very good leaving group. An SN2 reaction will also be favored if it has a very good leaving group. So alkyl iodides will both be better at SN1 and SN2 than alkyl chlorides. Okay? So you got to look at these other pieces. Solvent, nucleophile. Is the nucleophile strong? Is it weak? Is the solvent polar protic or polar aprotic? Okay, so you got to know all of those pieces.
And you said when it's polar aprotic, it's naked?
The nucleophile will be more naked, yes, in polar aprotic solvents. Okay? So all of this to say, you gotta think of it like this. Polar protic solvents like water and alcohols favor SN1. Polar aprotic solvents favor SN2. Can I do an SN1 in polar aprotic solvents? Yes. But the reaction would be sped up if I used a polar protic solvent. Okay? So keep all that in mind. So, here's a whole list of things that we can actually make by these SN2 reactions. Okay, so we're taking some alkyl halide. All of these are going to be made by SN2 reactions. Here's my nucleophiles, right? So if I take a primary alkyl halide and I react it with hydroxide, I get an alcohol. If I take a primary alkyl halide and I react it with what's called an alkoxide, I get an ether. If I take a primary alkyl halide and I react it with acetate, for example, I get an ester. If I react a primary alkyl halide with cyanide, I get what's called a nitrile. You know the gloves you use in the lab? They call them nitrile gloves. That's the functional group in nitrile gloves. Okay, they're very chemically resistant. And they're made by reacting some type of molecule with cyanide. Okay? And so you're actually wearing cyanide-containing gloves. And that's kind of odd for people to think about because people think of cyanide as being very poisonous. But not when it's bound to another carbon. If we take a terminal alkyne and generate the anion. We can make new carbon-carbon bonds here and make what's, a new alkyne. We can use azide and make azides. We can use ammonia and make amines. We can use thiolate and make thiols, so on and so forth, okay? What you need to know about all of these, right? All of these are really pretty good nucleophiles. Hydroxide's a good nucleophile. Alkoxide's a good nucleophile. Cyanide's a good nucleophile. Azide is a good nucleophile. Thiolate is a good nucleophile. Most of them, except for the amine, right, are negatively charged. So all of these things are going to favor an SN2 reaction, especially if we're reacting them with something like a primary alkyl halide, okay? All right. So that's the SN1 and SN2 piece. Now, there's another thing that you need to know about reactions of alkyl halides, and that is that they can undergo elimination reactions. So you can take an alkyl halide and you can eliminate the atoms H and X and get a new pi bond. This is exactly the opposite of the addition reactions that we learned about in chapter 5, I think, right? Where we took an alkene and reacted HX and got an alkyl halide. We can exactly do the opposite, okay? Notice what's happening. Tell me what's happening with these arrows in your own language.
We're breaking the hydrogen bond.
What hydrogen bond?
The one on the first C.
Okay, so we're breaking that carbon-hydrogen
Yeah, the
bond.
carbon-hydrogen.
Okay, and then what else?
And we're adding it to the carbon-carbon bond.
Okay, so those electrons are going between the two carbons. Very good. And what else?
And then the B is attacking where the hydrogen was.
Okay, so we're going to form a BH bond.
Yeah.
Okay, and what else?
And then the CX bond is going to break.
Okay, that's right. And this all looks like it's happening at the same time, right? All right. This is called a beta elimination reaction. Why beta? Because the carbon that bears the halogen is always called the alpha carbon, by definition. And any carbon that's attached to it is the beta carbon. So we're removing the hydrogen from only the beta carbon. That's why we call it beta elimination. Okay? So we are eliminating HX to form a carbon-carbon double bond. Okay? Now what's B with a pair of electrons?
Boron.
No. I mean, I can see why you would say that, but no. What does it mean here? Means base. It's just an abbreviation for base, right? So if I was to take what Selena said and now put it in my own words, I would say that a base is abstracting a hydrogen from the beta carbon, forming a carbon-carbon double bond while the leaving group leaves, right? That's how I would word it. And we get a new carbon-carbon bond between the alpha and the beta carbons. It's a very predictable reaction, okay? But you'll notice you've got things leaving, you've got things forming, all this kind of stuff, okay? Now wait a second, B with a pair of electrons, couldn't that also be a nucleophile?
Yeah.
Good, so what distinguishes a base from a nucleophile? Okay, does have to do with basicity, that's true. Bases only abstract hydrogens. They don't react at the carbon, okay? And here's something that's going to kind of blow your mind a little bit. But you need to memorize this. All nucleophiles are bases. All nucleophiles, by definition, are bases, Lewis bases. But not all Lewis bases are nucleophiles.
All
Okay.
nucleophiles.
Because remember, a Lewis base is nothing more than an electron pair donor, right? That's all a Lewis, that's the definition of a Lewis base. All nucleophiles have been donating their pair of electrons, but they've been donating it to the carbon. And so what we call those are nucleophiles.
So all nucleophiles are Lewis bases, but not all bases are nucleophiles.
That is correct. That is absolutely correct. Okay? So as you might imagine, some nucleophiles might give you a mixture of products because they may sometimes function as a base. We'll talk about that as well. Okay? Here are the common bases that are used in this so-called dehydrohalogenation. That is just the abstraction of HX to form a carbon-carbon double bond. Sodium or potassium hydroxide, sodium methoxide, sodium ethoxide, and potassium turbotoxide are common bases in these dehydrohalogenation reactions. Okay? And these elimination reactions, or beta elimination reactions. Use whatever word you want. These are nice, common solvents that are used to do this. But I just showed you examples of where hydroxide can function as a nucleophile.
Yeah.
Well, how do I know if hydroxide is going to function as a base or a nucleophile? It's going to depend on solvent. It's going to depend on reaction temperature. It's going to depend on a lot of things. We'll talk about it. Potassium turbotoxide, however, is one of those bases that will, for the purposes of this class, never function as a nucleophile. It is a non-nucleophilic base. All it will do is abstract hydrogen at the beta carbon. Because that tert-butyl group is big, it gets in the way, it won't let that oxygen get very close to the carbon. So all it can really do is abstract a small little atom like hydrogen. Okay? Now here's an example where we're taking tert-butyl bromide. We are reacting it with sodium hydroxide. Okay? I know that sodium hydroxide under these conditions will not function as a nucleophile. And how do I know that? I know that because my, at least in an SN2 reaction, let me rephrase that, because this is a tertiary alkyl halide. Okay? But hydroxide can abstract a hydrogen atom from the beta carbon. Notice we've got 1, 2, 3 beta carbons and they're all identical. So if I abstract this hydrogen, I get this product. If I abstract this hydrogen, I get this product. If I abstract this hydrogen, I still get that product. Only one alkene is possible in this particular reaction. Okay? However, when I look at 2-bromobutane, those beta carbons are no longer identical, are they? What's different about them? What's different about beta 1 versus beta 2?
Beta 1 is primary.
Okay, the number of hydrogens attached, right? So this beta 1 has 3 hydrogens attached to it. Beta 2 has 2 hydrogens attached to it, right? And so when we do the chemistry, we do the reactions, we end up with 2 different products, right? We can end up with a carbon-carbon double bond between alpha and beta 1, which gives this molecule. How would you name that? 1-butene. How would you name the second one?
2-butene.
2-butene. They have different names. They are different products, right? Which one would you think forms in greatest amount? Is it equal? Is it unequal? Okay. Why would you say equal?
Is it 2-butene? Is it 2-butene because of
No,
the
it's
carbons? Is it like because it's because that beta 2 is attached to 2 carbons and 1 is attached to 1?
Turns out it is unequal, and it turns out that the one on the right, the 2-butene, is the one that forms in the major product. It has to do with the more substituted alkene is the more stable alkene.
Yeah, that's what I was trying to say.
Yeah, just like the more stable carbocation is the more stable carbocation, the more substituted alkene is also. This is called Zaitsev's rule. Zaitsev's rule says that that the beta carbon with the least number of hydrogens loses the hydrogen. Now, of course, the beta carbon has to have at least 1 hydrogen, right? But if I look at beta 1, I see 3 hydrogens. I see beta 2, I see 2 hydrogens.
So
Beta 2 is going to lose.
it's like the opposite of Markovnikov's rule.
Kind of is. That's exactly right. Yep. And it should be, right?
Yeah.
Because of what we learned. We learned that this is exactly the opposite of that reaction. Okay? We've got about 8 minutes left, so we'll finish up this slide and then we'll finish this up on Wednesday and get into the next chapter. On on Wednesday. You can't expect a quiz on Wednesday just because I have to have one for the week, but it won't be on anything that's passed. So it won't be on much on, let me put it this way, I won't ask about elimination, okay? SN1 and SN2 is what I'll limit the quiz to. So, just like we have SN1 and SN2, we have two types of elimination. We have E1 and E2, okay? The E2 mechanism, what do you think the rate's going to be dependent on?
Two of them, like two, like the
Both the base and the.
yeah.
That's right, the base and the alkyl halide. Yep, just like the SN2 reaction. E1,
Just
Unimolecular, so only on the starting material?
yep, that's right, only the alkyl halide plays a role. So do you think the mechanisms are the same? No. And in fact, the E2 mechanism looks kind of like the SN2 mechanism, and the E1 mechanism looks like
Yes.
the SN1, and in fact, it does have a carbocation as its intermediate. Okay? So these are different, and what you will find quite frequently is that these reactions can compete with each other. You can have, I've run reactions before where I wanted an SN2 reaction to happen, and I get mostly the SN2 product plus some elimination, because SN1 and, or excuse me, SN2 and E2 competed with each other. Okay? And so what did I do? I went in and I played with the different solvents to try to favor one over the other. Okay? You can do a lot of little tricks that you learn in chemistry. But these things will compete with one another. And this is going to be the bane of this piece of this chapter for you all. There are problems that ask you to predict. Is this most likely going to be an elimination, or is it going to be a substitution? And so if you look at the bases and the leaving groups and the solvents, you can usually come up with a nice way to predict, right? So, especially when you look at something like, oh, that's got a base that's not doesn't function as a nucleophile, that's going to be an elimination reaction. So you'll be able to do that pretty easily. So, we will pick up on Wednesday by doing some more examples out of this chapter, which will all be elimination based. So we've technically finished this chapter, other than doing some example work. We'll pick that up on Wednesday. We'll get into chapter, what is the next chapter? Chapter 8. And we will have a quiz on Wednesday. Have a great day, and I will see you all later. Oh yeah, by the way, you will be getting your in-class stuff back in lab. And if you have a yellow check mark on it, you got all the bonus points. So I have put the solutions to that in the quiz solutions thing in Canvas. So please take a look at those and let me know if you have any questions.
They did it. Yeah, trust one of the